Let me. Okay. So we are glad to have Zohreh Davoudi here to introduce us on the road to quantum simulating QCD. So I will first introduce Zohreh. Zohreh Davoudi completed her undergraduate and master studies in Iran at Sharif University of Technology before moving to the US to continue her studies in theoretical physics. She received her PhD in 2014 from the University of Washington in Seattle, and shortly thereafter joined the MIT Center for Theoretical Physics as a postdoctoral research associate. In 2017, she joined the Department of Physics at the University of Maryland as a faculty. She was also affiliated with the RHIC research program until 2020. Her research involves studying strongly interacting systems, such as hadrons and nuclei, using analytical and computational methods, including effective field theories, lattice QCD, quantum simulation, and quantum computing. Her work is recognized by the US Department of Energy's Early Career Award, Alfred P. Sloan Fellowship, and Kenneth Wilson Award for Excellence in Lattice Gauge Theory, 2018. So I think her talk will be very exciting. So let's start, please.
Thanks very much. Thanks very much for the nice introduction, for inviting me to this very interesting series. I'm glad to be here and be talking about quantum simulation and quantum computing for research in quantum chromodynamics, or QCD, of course. We are here because we care about QCD. We care about understanding various aspects of a strong interaction in nature that are still hidden to us. And therefore, I'm gonna try to justify we might need new computing and simulating technologies to be able to uncover some of those still remaining questions in QCD research. So I guess this audience doesn't need introduction to why QCD is important and why QCD problems are difficult. But let me just say that the beautiful world of quarks and gluons and the world of complexities around us is pushing the frontiers of theoretical, experimental, and computational abilities to date. And that's why we are here. Importantly, if we want to address questions theoretically in the realm of QCD research, we have to do simulations, in particular perform non-perturbative theoretical calculations. But even simulating a single proton means that we are solving an infinite quantum body problem. This is the reason being that quantum mechanics and relativity are both in play and interactions are strong. So we're dealing with a strongly interacting quantum field theory. Of course, there is a program, a very successful program that has been put together to be able to simulate or compute quantum chromodynamics in order to learn about the physics of hadrons and nuclei and dense matter, and it's called Lattice Quantum Chromodynamics, or Lattice QCD. I'm not going to tell you a lot of details about what this program is about, how it's built, and what it does, but I want to give you a flavor of what kind of frontiers exist in a Lattice QCD program that would allow us to be able to simulate this difficult problem of QCD first principles, okay? The reason I'm going to do this is that, as we will see, there is a very exact parallel between these frontiers, these different prongs of the program that have been built over many decades, and what we envision are going to be the frontiers of the quantum computing and quantum simulation program for Lattice QCD. So I'm going to spend a few minutes to tell you what we have, we need, and we have developed in classical computing of lattice chromodynamics, quantum chromodynamics, and therefore we can see why we need a similar kind of program to be put in place to be able to do quantum computing QCD. So what are those different prongs of the classical computation or Lattice QCD program? Well, we needed a lot of theory developments, algorithmic developments, and at the same time, hardware implementation, benchmark, and even co-development that came along to enable this successful program to give us observables in nature that we care about from first principles. Let's talk about theory developments, just the kind of questions that at the time when this lattice gauge theory method was developed, let's say in 70s and 80s, people had to think about, and even to date, we have to think about some of these theoretical questions. How to define QCD or even a standard model on a finite space-time grid, because that's how we can compute things with finite computational resources. We cannot compute infinite dimensionals or the Hilbert space of quantum field theories. We have to make them finite dimensional. And the way that we do it, we put this on a finite grid. And of course, if we do that, we have to ask the question of how do we preserve and recover symmetries like gauge symmetry, chiral symmetry, rotational symmetry. There's been a lot of important theoretical developments along the way that have allowed us to really address questions of this form. We had to understand how to take infinite volume and continuum limits of observables so that we can compare the quantities with what we get from experiments or what we need to predict for nature. And therefore, we needed to quantify systematic uncertainties. A lot of time, there were a lot of theory work and thinking that went into understanding and quantifying these systematic uncertainties. And we needed to also understand how to obtain dynamical quantities like scattering amplitudes, because the way that we perform these calculations was to go to imaginary time. Because the computational method that we're using is based on Monte Carlo sampling, we had to actually do this. And I come back to this in a moment to see what kind of limitations that would impose on us. But in any case, there had to be some theory work to be done to understand how do we extract things like scattering amplitudes of 2 hadrons and 3 hadrons and reaction rates and things like that that are intrinsically Minkowski real-time observables. So our program in Lattice QCD now has answers to many of these questions, and we're still continuing to explore them. There's also algorithmic development. What does that mean? Well, our community had to figure out how to do quantum field theory simulations. So the way that we had to do this was using important sampling methods. And what is sampled are vacuum gauge field configurations. And then observables are being calculated in the background of these gauge fields. Once you do this, we had to kind of figure out how to evaluate the propagations of the quarks in a space and time, because our computations are first principles. We only have quarks and gluons in the simulations. So we have to understand the dynamics of these quarks and gluons, right? The gluons, we deal with them by importance sampling them, and the quarks, we have to deal with them by understanding how they propagate in a space and time. This becomes the question of inverting very large matrices in the end of the day, by the orders of hundreds of million by hundreds of million dimensionality. And then we have to also calculate correlation functions to be able to have access to physical observables like the energy and masses and matrix elements. This involved weak contractions of the quarks between the interpolating operators for the source and sink. And I'm not going to go into the details of this, but in the end of the day, this was also a very complicated computational problem. And people have to come up with algorithms that would perform all these different steps, from importance sampling, inverting large matrices, and the problem of contractions in the correlation functions very efficiently. And that's why algorithmic development have been very important along the way. What else? Well, we had to also think about hardware, and we had to adjust our calculations to the state-of-the-art hardware that came along. And in some cases, we had to also think about how to do a co-design process with the people in the hardware industry in classical computing to be able to make these computations more efficient. And This is an example that I always like to show. This is kind of a screenshot from a paper from about 40 years ago by the Columbia group, Norman Crest and collaborator, where in this paper, they try to figure out how to build sort of an computing cluster that can perform multiplications of these SU3 matrices more efficiently. And kind of this is a picture of what they had in mind in terms of these multiplication, additions, and sorting saving things in the memory and kind of getting access to them with all sorts of networks. So even the theorists at the time, these lattice gauge theorists, had to think about how to build and adjust the hardware so that they can make them more suitable for the task of computing lattice gauge theory computations at the time. Another thing that I want to mention over here is that, remember, at the time, which was like 4 decades ago, what we're talking about is the state of the art was computing pure gauge theories on lattices that were only 4 by 4 by 4 by 4 space-time dimensions. And this was already kind of quite impressive at the time, given the amount of computing that was available to them. And we're talking about computing powers that was kind of 10 orders of magnitude slower than the current supercomputers that we have available for these programs. And we're talking about only a few kilobytes of memory, okay? So our community has come a long way because not only theory and algorithm have progressed to where they are today, but also at the same time, hardware has also had an impressive sort of advancement in both memory and the speed. So this is something that I want you to keep in mind when I talk about quantum computing for this program. We are kind of at the same place that we were maybe 40 years ago in terms of classical computing lattice gauge theories. So we don't get to be discouraged, given that we are a community that have gone through this process, and our important science really depends on how computing technology also gets developed, and we want to also play a role in developing this technology or co-developing this technology. So again, the kind of questions that people had to kind of figure out was what kind of tasks can be parallelized, what kind of tasks can be done in series, what are the memory requirements, what kind of node connectivity is required, and then how they should take advantage of new computing technologies that come along, like GPUs. What part of the computations are more suitable for given architectures? Should we put important sampling on the CPUs and maybe propagation of the quarks on GPUs, or vice versa? Kind of questions like this are the kind of questions that we still, even today, have to think about, right? In the classical computing lattice gauge theory. So with all these heroic theory, algorithm, and co-design efforts that have been going for many decades, and having access to hundreds of millions of CPU hours and even now GPU hours on the largest supercomputers in the US and also internationally, this has led to many impressive results. I'm sure many of you are familiar with the kind of results that Lattice QCD program is producing, for example, for a heavy ion program, but also for other frontiers in nuclear and high energy physics. I'm going to be a bit selfish and kind of showcase 4 results from my collaborations, because I think it's important to realize that we can do also computations for nuclear structure and nuclear reactions. Okay, so not only you can do single nucleon observables and single hadron observables, we have even gone beyond that sort of single hadron physics and are able to look at things as complex as in nuclear reactions. So let me kind of very quickly highlight these results, because I'm not going to talk about classical computing progress, but I'm going to sort of switch over to the quantum computing progress. But let's remember that now we know how to perform first principle QCD computations of a process like PP fusion at low energies. We can even look at exotic processes like neutrino fold and even neutrino-less double beta decay in the 2 nucleon sector, which is very important, obviously, for neutrino-less double beta decay program in the nuclear physics community. We can look at nuclear effects in the response of a nucleus to external probes. For example, if you're using a nucleus in probing dark matter in your dark matter detection experiments, you are going to need the input about how much of the nuclear effects are coming for various different sort of currents of, for example, the scalar current for the case of the dark matter detection, and whether that can be described as just single nucleon responses or there are some multi-nucleon correlated effects. Of course, Lattice QCD would give us an access to these kind of questions from first principles. This is kind of a starting point for light nuclei that we kind of probed in this paper that I have mentioned over here. We can also look at interactions among baryons, for example, among baryons that contain strangeness and so on, because these are the kind of interactions that are not very well constrained by experiments. But of course, we know that the knowledge of these interactions are helpful in refining our understanding of the dense matter and the role of strangeness and other degrees of freedom in the, for example, core of neutron star and the equation of the state of the neutron star. So that's why we have had the first step towards understanding baryon-baryon interactions from first principle and even identifying the expected or predicted symmetries in the large N limit, and even discovering more extended symmetries from these calculations. So if you're interested in the kind of this frontier and what kind of progress that we made over the past few years, you can look at this review that we put together with my collaborators within the NPL QCD collaboration. But I don't want to limit this talk to this kind of progress. I just want to say that Lattice QCD using classical supercomputers have been really supporting a multi-billion-dollar experimental program, not only in nuclear physics, but also in high energy physics. It's kind of the slide where it kind of shows the impact of Lattice QCD on hadron spectroscopy, fundamental symmetries, nuclear structure and astrophysics, and hadron structure, and really sort of supporting a range of experiments internationally. So this is great. So this 40 years of effort is sort of paid off, because it's now starting to really be important in terms of phenomenology and understanding of nature and supporting experiments, which is really sort of why this committee has been pushing forward for a long time. But unfortunately, that doesn't mean that we're all set, right? So this is not everything that we hope to get out of this program. I can stop right here, and maybe if there are questions about this part of the talk, I'll take it right now and then give you a moment to kind of absorb what I just said about the classical program before starting to motivate the quantum computing program. Any questions?
No.
Okay. All right. So looks like everything is clear. So let's talk about why Lattice QCD program using classical supercomputers is not really enough. Okay. I see a raised hand. Bernd, please.
Yeah, actually, sorry, I have a question here. To what extent is what you call classical computing, which means classical digital computers as a use of computing of lattice gauge theory, to what extent is that full calculation of the quantum theory, and to what extent does it not take into account certain quantum effects? So in other words, if we do and have a quotation of a result from the classical computation, as you call it, to what extent is that a result of the full quantum field theory, and to what extent are there approximations?
And that's a very good question. I think I should have made this very clear that what we are simulating is the true quantum mechanical relativistic effects in a quantum field theory, but only using classical computers. So our computations are not limited to just giving us certain classical limits or models of the QCD. They only limit us in the type of observables that we can look at. For example, we can look at static properties, like the spectrum of the states or certain matrix elements. And the reason being that they are still fully quantum mechanical features, but we have access to them from an Euclidean quantum field theory. So only for observables where we can figure out how to do a rigorous analytical continuation or other methods to be able to get access to the same quantities in Minkowski quantum field theory, then we work on those quantities using this method. But other than that, it has all the quantum effects. We're not making any approximations about leaving out some of these quantum correlations. So very good question. Okay. And that's where I'm going with this, because I'm gonna say that there are certain quantities that we cannot compute using the method that we're using today. And the reason that we're using this kind of method is that we're limited to these digital classical computers, okay? So it's kind of the question of the method, but the method is also limited by the type of hardware that is available to us at the moment. Okay, so let's talk about why lattice QCD is limited. Well, unfortunately, we can't just take our favorite nucleus and start to simulate it from QCD degrees of freedom. There are three reasons that I can enumerate for this. One is that the complexity of the systems grows factorially with the number of quarks. Let's say you're interested in your favorite isotope, whether it's radon or radium or germanium, for whatever experiment that we're dealing with, for example, neutrino star beta decay or dark matter detection experiment, and ask the question, I'm interested in certain matrix elements of various currents in this large nucleus. Can I just go ahead and compute that with lattice QCD method? Unfortunately not, because remember, we start from quark and gluon degrees of freedom. And in particular, in order to interpolate a state that has quantum numbers of a large nucleus, then we're dealing with the complexity that grows factorially with the number of quarks. And then do your math, and you see that really fitting a problem of that type on a classical computer is going to be really challenging. It's not going to happen in any time soon, okay? We are also dealing with another exponentially bad problem, and it's called the signal-to-noise degradation problem. Again, the way that we do computations are in imaginary time, and it turned out that the correlation functions of even a single nucleon, not even a large nucleus, even a single nucleon or a single baryon, has a problem that at large Euclidean times, the signal would really lose compared to the noise in the system. There's something about the features of the QCD spectrum, the fact that there are these light pion degrees of freedom that contribute to the noise correlation function is really the reason behind this. But in the end of the day, we're dealing with a problem where our signal really degrades, and the degradation in the exponent really is proportional to the Euclidean time, is proportional to the number of nucleons in the nucleus, is also proportional to sort of let's say these two factors are more important, and there are some pre-factors and so on that people have thought about. But in the end of the day, again, in order to resolve the signal, we have to have exponential increase in our statistics to be able to do this. And number three is the fact that we need to have very good precision to be able to really resolve the energy gaps of a large nucleus. The reason being that as the nucleus become heavier and heavier, as we know, the excitation gaps becomes smaller and smaller. Even for the smallest nucleus possible, right, the deuteron, we're talking about 2 GeV of mass, but only 2 MeV of binding energies, right? So we're talking, when it comes to the larger nuclei, we're talking about orders of magnitude difference between the excitation gaps and the ground state energy. And we have to be able to resolve these energy gaps. Otherwise, we don't know what we're doing, and we're dominated by the excited state effects and so on. So as you can see, we are limited to probably the few nucleon systems in our computations. And beyond that, it seems a very difficult problem with the current methods and the current computing hardware that we're limited to, okay? So the other class of problems are problems that really have also a sign problem. I talked about signal to noise problem. which is kind of very closely related to the sign problem. But you can also think about sort of the generic class of the sign problems that limit our calculations. For example, I'm sure everybody in this audience is very much interested in the question of the QCD phase diagram. Why can't we just introduce a fermionic or quark chemical potential into our QCD action and be able to really learn about the phase diagram of QCD at finite densities? The reason is, of course, again, that we do a path integral formulation and we sample configurations based on a weight that goes like e to the minus s. This is a positive definite weight. The reason being that we have gone into Euclidean space-time so that we can define this kind of well-defined positive weight and work with it. As soon as we introduce a chemical potential, your action becomes complex, and even this trick of Euclidean sort of weak rotation is not going to save us from this severe sign problem. So unfortunately, we're very much limited to the regions of the phase diagram that is very close to the temperature axis and cannot really probe these more sort of exotic phases of QCD that we hope to get first principles knowledge of. Another class of problems that have severe sign problems are real-time dynamical problems. For example, if you're interested in the evolution of matter from first principles, again, this is a problem close to the heart of this community, really understanding how matter evolves as a function of real time after the collision of these heavy nuclei or after the Big Bang, how it thermalizes and equilibrates and hadronizes and freezes out, and all sorts of interesting processes that we know are happening after these very extreme processes. Unfortunately, as we know, a lot of modeling goes into understanding and making predictions, right, for experiment. The reason being that, again, our first principle QCD simulations do not allow us to look at something like real-time process. The reason being that if we go to real time, then we are dealing with e to the is as the weight of our path integral sort of sampling weight, okay? So again, as I said, we lose access to the direct access to these dynamical properties. And in principle, any quantity that we can define using Minkowski time, all sort of dynamical response functions, transport properties, hadron distribution functions, and so on and so forth. These are the kind of quantities that are defined by Minkowski signature of space-time, and any effort to kind of get them from Euclidean signature is going to be indirect and very difficult, right, as we know. So you may say, for the kind of time evolution questions that I'm posing here, Hamiltonian formulation and Hamiltonian evolution might be a more suitable approach. And of course, the answer is yes, because once you have the Hamiltonian of the system, you have the state, you just act on the initial state by e to the minus IHT, and that would give you the information about the later stages of the process. Unfortunately, the problem is that, as we know, we're dealing with very large Hilbert spaces in lattice gauge theories and in QCD. So if you're attempting to fit this problem into a classical computer, this Hamiltonian, this Hilbert space, that's kind of a dead end in principle. And this is the reason that despite the fact that we had the Hamiltonian formulation of lattice QCD, even in 70s and 80s, the program really didn't make that much advancement. The reason being that we didn't have, and it still don't have, large enough classical computers to fit this problem. There's been a lot of progress in recent years in trying to do classical Hamiltonian simulation using tensor network methods. And they are impressive. They are actually building simulations in higher dimensions. For a long time, they were limited to lower dimensions. So they're actually making quite a lot of advancement. The problem being that they're still limited with their computational method by the amount of entanglement that is generated in the system. So if you're dealing with problems that are in real time, high energy, high in elasticities, we know that entanglement growth is beyond and the scaling that is required for these tensor network methods to work and be efficient. So it seems like even though we might have efficient Hamiltonian simulation approaches in classical computers using tensor network, they are not the final solutions, right? And we need something more. So this is really an opportunity to explore new paradigms and new technologies. And that's why we are in this community turning into quantum simulation. So again, I'm going to pause here and see if there are questions. And in the meantime, if you're interested in more motivations of physics drives for this program of quantum simulation, I have given here 2 planning documents that I was involved with for both long-range planning process in nuclear physics this year, and also a SNOMAS planning process for particle physics last year, where we really sort of spell out why we need this program. Yes, Bernd?
Sorry to ask another question here at this
Sure.
stage. Before you come to the quantum computers, the issue, one of the problems that people have faced over the decades with the Hamiltonian formulation of quantum field theory is that the renormalization program is much more difficult because you're breaking effectively Lorentz invariance. And so is it understood how, even in principle, to carry through that Hamiltonian framework of simulation of QCD independent of the practical method?
Yeah, so maybe when I talk about Hamiltonian formulation, a couple of the slides, we can come back to this question. Would that be okay? Because I think it's an important question. And I don't have a lot of detailed explanation to give in these slides, but I can tell you what our committee is thinking about at the moment. This is definitely an important question, and I'll get to it. That's
okay. Thank you.
Great. Good. All right, so the reason we think that there is an opportunity here is that there is a range of quantum simulators and quantum computers even that are out there with varying capacity and capability from in universities, in companies, in national labs, in various different countries, and they use a range of physical systems to build this system, from atomic systems, condensed matter systems, laser-cooled polar molecules, optical quantum computing, and so on and so forth. So this is a really interesting and expanding sort of area of research and development. And we will see how things would develop. But even sort of in the past 10 years, there's been huge progress in terms of hardware technologies. By no means we are close to having fault-tolerant larger-scale quantum computers yet, but the sort of the advancement in hardware has been impressive. So we can imagine that in a matter of a couple of decades, we will have really capable machines that we can use to perform our research problems and endeavors. So that's why we think in the QCD community, we need to pay attention and we need to see what can we do with these systems once they are available, okay? So you may ask the question of how similar QCD computations are to quantum chemistry simulations. Why am I singling out quantum chemistry? Because it turned out that this is the community that recognized the importance of quantum computing in their research quite early on. There's been quite a lot of developments in that community already in terms of understanding algorithms, how well they scale, and so on and so forth. And of course, there is a huge interest in quantum chemistry and material science because of the drug designs and battery design and so on. So there's really a commercial value in being able to apply quantum computers to quantum chemistry problems, for example. And so that's why I asked this question of, can we just use those developments and build something for QCD? The answer is yes and no. A lot of sort of technologies are similar in terms of algorithmic development, so we don't have to reinvent the wheel. But on the other hand, we're dealing with kind of different physical problems. If we want to start from the standard model and simulate problems that of interest in nuclear physics, And we are dealing with bosonic and fermionic degrees of freedom. They're dynamical, they're coupled, and they exhibit both global and local gauge symmetries. But importantly, these are relativistic systems. We're not dealing with non-relativistic quantum many-body systems like in other areas or disciplines. We really have these specific sort of quantum field theories, and therefore particle number is not conserved. Vacuum state of the theory is non-trivial and is a strongly interacting theory. And therefore, we have to make sure that we build all these features into the computation, okay? So that takes me to this slide. As I said, there's a very close parallel between classical developments of QCD simulations and now quantum developments in QCD simulations, because we think that a quantum simulation program for QCD is also going to be a multi-frontier, multi-prime program. It's going to involve a lot of theory, algorithmic, but also hardware implementation and co-design efforts to become successful. And it's going to be probably a long road, but one thing we learned from Lattice QCD program using classical supercomputers is that patience is important, and it's important to really sort of move with the developments on the hardware and algorithm at the same time. So let me give you a few examples of these different frontiers. I'm going to, of course, focus more on my work and the work of my collaborators. So it's not going to be a very comprehensive review, but my goal here is to give you a sense of what each of these frontiers would involve, what kind of questions we have to ask, okay? And depending on the time, I try to maybe skip over some of them, just to sort of give you a taste of some of these frontiers. We don't have to really go into a lot of technical details here. So in terms of theory developments, how do we formulate QCD in the Hamiltonian language? And so this really goes back to the question that Bernd was asking. We have to now start to ask these important questions about symmetries and continuum limits and renormalization and so on and so forth. And that's why this program also needs its own theory developments. And it's even more important because when we are talking about the Hamiltonian language, we're talking about the fact that there is more than one Hamiltonian formulation, there is more than one Hamiltonian basis or Hilbert space basis or representation. In the end of the day, once we take the continuum limit, we should recover the same physics. But of course, there are multiple different ways of defining the theory on the lattice, and particularly in the Hamiltonian language, and be able to recover the same physics. But we have to understand which one of those methods or formulations are more efficient. What are the most optimal bases to take so that we need less resources to go to the continuum limit? How do we preserve symmetries? How much should we care about retaining gauge invariance? And importantly, how do we quantify systematics, such as finite volume effects, discretization effects, and also new things like we have to truncate the Hilbert space of the bosons, bosonic field in bosonic field theories. Sometimes we do time digitization. So although our time is continuous, we still digitize them in the algorithm. So we really need to understand and that we recover the physics that we're interested in, the continuum infinite volume limit, again, in this program. And there, in all these different directions, people are working very, very hard to really have some answers. So let me go into some of these aspects. Definitely not all of them, but because I want to get to more sort of algorithmic side of things as well. But let's talk about Hamiltonian formulation. Of course, we know that Koget and Susskind wrote a Hamiltonian a few decades ago. In fact, at the same time that Wilson was writing his own action-based lattice gauge theory, Koget and Susskind thought, well, let's just talk about Hamiltonian formulation. So they wrote a lattice Hamiltonian that had 4 types of terms. Again, I'm not going to go into the details of this equation, just to remember that we have fermions and bosons. Fermions are sitting on the sites. Bosons are connecting the fermions on the sites. There is a hopping of the fermion that is assisted by the gauge links. There is a fermionic mass term, and there is the energy that is stored in the color electric field and the energy that is stored in the color magnetic field. This term in particular is called a plaquette term or plaquette interactions. So all Hamiltonians of gauge theory, no matter what, is going to have these kind of 4 types of terms to correspond to what we know in nature. So what's the problem? We have the Hamiltonian. Well, the first problem is the fact that this is an infinite dimensional Hilbert space. So it's not going to fit even into a quantum computer, no matter how large that quantum computer is. So theoretically, we have to understand, given the basis representation that we pick for our gauge fields and electric fields and so on, how fast we recover the infinite dimensional limit of the theory, okay? So that's why there's been a lot of both theory work as well as some analytic work to try to understand the scaling of at least low energy and low time observables as a function of the truncation that you put on the cutoff in the Hilbert space. Some of these truncations, you might put it on the group element basis. That's the basis where the first term is diagonal, because electric field and the gauge links are conjugate variable to each other. We can't simultaneously diagonalize them. So we pick one of those bases. And once you pick one of those bases, some of the interactions are going to be diagonal in that basis, but some other interactions are going to be off diagonal in that basis, right? So that's why there are choices. So for example, in this paper, they look at the group element basis. In these other papers, they look at irreducible representation or electric field basis for various different theories. And what we observe is that at least at a fixed lattice spacing or discretization, there is an exponential convergence to the infinite dimensional limit of the Hilbert space. Unfortunately, it becomes polynomial as you try to take the continuum limit. And this is, again, goes back to Bernd's question that how do we make sure that we recover the continuum limit with the right sort of scaling. This is really sort of one of those questions that we didn't have to deal with before. We only had discretization effects, but now we also have the truncation effects. And we have to understand as we take the continuum limit, what is the scaling of this truncation, whether we remain in the same universality class as the theory we're interested in, which is QCD in the continuum limit. So people are really looking into questions like this. There's another aspect of the Hamiltonian formulation that we have to be careful about, because the way that Hamiltonian is defined, remember, and when we talk about Hamiltonian formulation, as Bernd mentioned, we take the time to be continuous because that's really a parameter in the time evolution operator. So we only have the space-time lattice. Okay, so that's why these fields are defined on just a space lattice, not time anymore. The other aspect is that we need to pick a gauge, right? There is some gauge redundancy. The gauge that is being picked here for the Kogan and Susskind formulation is a temporal gauge, meaning that the zeroth component of the A mu field is set equal to 0. Okay, and we know that there is no dynamic in the A0 field, right? In gauge theories, in QCD, in QED, so that's fine. But that doesn't completely fix the gauge, right? So we still have the redundancy. Importantly, we know that there are certain sectors of the theory that are separate by the eigenvalues of the Gauss's law. And only one sector of the theory is really physical. But that sector is the sector that satisfies the Gauss's law. Gauss's law is just a statement that the net charge that comes that is sitting inside sort of a surface is balanced by the electric field flux that goes out of that surface, right? Just the same thing that we had in the electromagnetism course. And now this is just generalized to a lattice system and to a non-abelian gauge theory, but it's still kind of the same thing. And this is kind of that statement, right? But what that means is that only a particular sector of the Hilbert space that is represented by this Hamiltonian above is physical. That's the sector that corresponds to the 0 eigenvalue of the Gauss's law operator. And in this case, there are multiple Gauss's law operators because we have a non-abelian symmetry, and therefore there are multiple generators of the symmetry. And the rest are really unphysical. So now you can imagine that if you're dealing with a simulation and you're encoding your Hamiltonian in a simulator or in a computer, there's a lot of redundancy, and it's not really efficient to simulate the entire Hilbert space where you only care about a small bit of it. You may start your simulation over here, and because of the Hamiltonian evolution being the sort of the symmetric with respect to that operation, you are going to stay within that sector. But remember, there are errors. There are errors associated with the algorithm. There are errors associated with the hardware implementation. So you can actually leak out of these Hilbert space, and that would be dangerous because then you're breaking gauge invariance. And if the amount of breakdown of gauge invariance is large, you may not even recover the same continuum physics anymore, because you may not be in the same universality class anymore, for example, right? So again, that's why it is very important to understand the amount of breakdown of gauge invariance that may occur in these simulations. Let me skip this. Just the point of this plot is to just say that the size of the Hilbert space over here is exponentially smaller than the rest of the system, even for simple non-abelian theories that you can imagine, okay? And even abelian gauge theories. Even though the size of the system, physical Hilbert space, is still exponentially large in the degrees of freedom, it is much smaller than the rest of the Hilbert space. So how do we deal with this problem? So it turned out that you can try to suppress this leakage to the unphysical sector by doing some theory work. And in particular, you can say, let me take my Hamiltonian and formulate it, particularly just in this sector, so that I don't have to even worry about the existence of these other sectors. So that's some of the theory work that you have to do. In this case, this is a work by my former postdoc and the current postdoc, and also the current students that have sort of extended this to SU3 gauge theories. You can actually build physical degrees of freedom on site on your lattice. I'm not going to go into the details of this, so that you kind of primarily within this sector. In other words, you solve all these non-abelian Gauss's laws on site. So you only deal with operators that create or annihilate physical states that satisfy the Gauss's law. So you just do your theory work prior to even thinking about simulating the theory. And that would mean that then you have still a local theory with physical degrees of freedom at the site. In order to make sure that the theory still remains local, you just introduce these non-local abelian Gauss's laws at the links. Okay, so that's a very short description of one formulation that has been developed to really deal with the question of redundancies and Hilbert space construction. Let me skip this again. This is sort of in a simple model, trying to figure out whether you get benefits out of a formulation that is physical, based on physical degrees of freedom. And in fact, you do by many, many orders of magnitude. So that's really important to do your theory work, to be able to really sort of build a Hamiltonian formulation that is more efficient, okay? Here is a slide to say that there are many different Hamiltonian formulations of gauge theories. People are rigorously looking into these things and trying to understand which one to pick for the quantum simulation program. I've mentioned a few names, no references here. You can ask me about the papers. There's a lot going on at the moment in the community. And you may recognize some of these formulations from Lightfront to link models, qubitizations, and dual plaquette bases, spin dual representations, prepotentials, the looped string hadron that I mentioned, group element bases, and so on and so forth. So you see that really sort of this question of understanding the truncation effects, the renormalization and continuum limits, how efficient they are in terms of encoding and so on. All of these come into play to understand the benefits of one formulation versus the other. And this is a really active field of research, okay? I didn't touch on the renormalization here, but maybe we can talk about this in a discussion, Bernd, because I see that I have maybe 5 minutes and I still half of my talk, not talking about half of my slides.
I think there is still 10 minutes.
10 minutes, okay, all right. So I still have two important things to say about algorithms and about the hardware. So let me very quickly give you a sense of what these frontiers are. So in terms of algorithmic developments, let's talk about digital quantum computers, because they're very similar to the digital classical computers that we deal with today, right? So we need to understand near and far term algorithms. We need to understand what are the errors that are occurred due to those algorithms. And based on those errors, be able to come up with realistic resource requirements for gauge theories. And then we have to do this in the context of those formulations and encodings that I talked about. We have to understand which one can reduce the qubit and gauge resources and give us the continuum limits more robustly and faster, okay? And we should understand whether we can develop gauge invariant algorithms, because as I said, breaking gauge invariance might be a bad idea. And then of course, we have to understand the question of state preparation and how to compute observables like scattering amplitudes, collision processes, and so on and so forth, okay? So these are the type of questions. Let me talk about a few of them just to give you a sense. So in a digital quantum computing, you are given a Hamiltonian that can be separated into a sum of local or semi-local terms. And then each of these terms, you just take them, you exponentiate them, and then you figure out how to represent each of these exponentiated terms into single qubit and 2 qubit operations. Because it turned out that there is a universality associated with only a finite set of single and 2 qubit entangling operations. In other words, any unitary can be represented with a very high accuracy in terms of only a finite set of single and 2 qubit operations. So the program of digital quantum computing is all about taking your Hamiltonian, separating it into the terms where each of those terms can be exponentiated separately. But because you are breaking these terms, you better do that for a small amount of time and then repeat those steps so that in the limits of very large number of Trotter steps, you recover the physics you're interested in. There are other approaches to digitizing time evolution operators, but this is the one that is most popular, okay? So then once you do that, you ask the question of how many qubits and how many gates are required to achieve certain accuracy in given observables. And importantly, are these algorithms scale optimally, meaning that do they scale polynomially with the system size, or do they still scale exponentially with the system size, in which case there's no difference between a classical computation and quantum computation. So we better try to find algorithms that are efficient, and in other words, they are polynomial in system size. There's been a lot of algorithmic developments for abelian and non-abelian gauge theories towards even higher dimensional theories, SU2, SU3, and so on. I'm giving some references here. In particular, I just want to mention that if you're interested in really sort of the detail or concrete ways of doing these exponentiations and decomposing into the single 2 qubit gates and understanding the errors and resource requirements. We had a paper a few months ago with my student and postdoc, where we really spell out what is required in coming up with circuit decomposition of these gauge theories, and then how do we make sense of various sources of errors. I'm going to skip this two details. Maybe this is an important slide, kind of giving you an idea of the kind of resources that we are thinking about at the moment that are going to be required for non-abelian gauge theories. Let's look at the plot that I have over here. One of them is the number of T gates, which is sort of the non-Clifford operations that are going to be costly in the fault-tolerant quantum computing. And this is a model which is just SU2 gauge theory in 1 + 1 dimension in this sort of physical formulation of the model using loops, strings, and hadrons. And what we show is that in this plot, taking the continuum limit of the theory and the bulk limit or infinite volume limit amounts to an order of 10 to the 12 T gates, these costly gates, okay? And tens to hundreds of thousands of qubits, okay? In terms of the number of entangling gates with not so small accuracy on the time evolution operator, let's say in the near term, because in the near term, we may have access to these systems with a large number of entangling gates, we're talking about 10 to the 6, 10 to the 7. So millions of gates are going to be required to take the continuum limit of the 1 + 1 dimensional SU2 gauge theory. So now you can imagine for something like QCD, this is going to be a much higher gate amount. And we can discuss where the cost comes and why is that non-abelian gauge theories are so much costlier than abelian gauge theories, and how do we make sure to really reduce the resource requirements by more intelligent algorithms. So that's why this area of research, algorithmic research, is very important as we make a leap into near-term and also far-term quantum computing. Let me skip analog developments. This is very important, but it doesn't seem that I have a lot of time to talk about it. I can just tell you just very quickly what the concept of analog is, but I won't go into some of the examples of what we have done to do an analog simulation of gauge theories. So analog simulation means that there is no gate, okay? You have a system, a physical system of atoms or a condensed matter system. You realize that it has similar degrees of freedom, or at least the degrees of freedom that can be representing the degrees of freedom that you're interested in. So you can have a mapping between the degrees of freedom, but also the Hamiltonian in that system can be engineered such that it mimics the Hamiltonian of the target system you're interested in. In that case, as soon as you start your experiment, and the system evolves just naturally, it's going to just represent the time evolution in the target system, obviously, right? So this is what is called analog. We're not digitizing time evolution operator, it's continuous, but that really requires a knowledge of the physical properties of these architecture that we're dealing with, and be able to come up with ways to engineer Hamiltonian such that it mimics the Hamiltonian of interest. Obviously, this is very difficult. There aren't many systems out there that can represent, for example, a complicated gauge theory. Okay, so that's why it's a very interesting program, but it has some limitations. And let me skip these the kind of things that you can engineer, for example, in trapped ion systems, be able to sort of simulate something like a U1 gauge theory in 1 + 1 dimension. But obviously, as we go into more complex theories, then this becomes very difficult. Okay, so that's why I'm going to come to this aspect of my talk in the maybe last 5 minutes and talk about, given the fact that there are these two approaches available to us, digital and analog. Digital is very costly at the moment. We don't have millions of gates and thousands of qubits to be able to do even simple gauge theory computations. Analog is also hard because we don't have systems that have Hamiltonians and degrees of freedom that mimic the ones that we're interested in non-abelian gauge theories, for example. And then what do we do? Okay, so that's why sort of understanding the hardware and doing a lot of implementation, benchmarking, co-design is important. The kind of questions that we ask in this frontier: what is the capability limit of the current hardware for gauge theory simulations? What is the nature of noise in given architecture, and how can it be best mitigated? Can we use our physics insights about a problem to do better noise mitigation for these systems? Can we co-develop dedicated systems for gauge theory simulations? That's really important because, as we said, classical simulations of gauge theory or lattice QCD really started by the people thinking about how to build computing clusters in such a way that are more suitable for gauge theory simulations. Should we also think about the similar co-design process for quantum hardware? The answer is obviously yes. And importantly, can we combine digital and analog ideas to facilitate simulations of quantum field theories in the near term? Okay, so let me give you very quickly examples of some of these things. So, for example, let's say we want to simulate an abelian U1 gauge theory, the lattice Schringer model, using a trapped ion quantum computers. In this case, because it's a one-dimensional theory, you can solve Gauss's laws, and you just end up with fermionic degrees of freedom that can be mapped into the spin degrees of freedom, it turned out. So that you have your fermions, you just map them to your qubits in the trapped ion system, you turn on your laser so you can induce the gates, and therefore you can simulate in a sort of Trotter expansion in a digital way this kind of evolution operator. And this is sort of in terms of the language that I introduced, the 2-qubit gates and single qubit gates. You have a bunch of operations. You build this circuit, you give it to your experimental friend, or you put it on the cloud for using the hardware that is provided to you by a company. And that's it. Then you will get the answer that you want out of this circuit. So this is sort of a time evolution in Schrödinger model, and this is a plot of the pair creation as a function of time, which is a very non-perturbative, non-perturbative dynamical process in a trapped ion system with just 4 qubits. Okay, so this came out in 2016 by a group in University of Innsbruck. It really generated a lot of excitement. And since then, there's been even more computations using the IBM superconducting circuits, more sort of advanced trapped ion systems at the University of Maryland, and work that we did last year. And the thing that I want you to notice is that we're still very limited with digital computing. This is a computation with 6 qubits, and we're talking about of the order of 100 entangling gates. Remember, I talked about millions of entangling gates to take the continuum limit of a theories like this, okay? And there's been also computations on small computations on the hardware for non-abelian gauge theories, both dynamic and the spectrum. So this is quite exciting. We know how to do these computations. We have the algorithms, we have the techniques and understanding of the hardware to be able to really simulate even SU to SU3 gauge theories in higher dimensions on a quantum hardware. But of course, these are very small simulations. We can also do them with our classical computers, even analytically, right? But this is progress, right? So really the final point that I want to make is really combining these digital and analog ideas, because as I said, digital computing seems to be costly for gauge theories. Analog computing or simulation seems to not be possible for QCD problems and certain non-abelian problems. What do we do in the short run? Well, it turned out that you can combine analog and digital ideas. So you still digitize the time evolution operator so that you can simulate with more flexibility any type of Hamiltonian that is local or semi-local. But at the same time, you don't limit yourself to just the qubit degrees of freedom, but also to other degrees of freedom in the hardware. If you have bosons or fermions, let's just take advantage of those. We can just limit ourselves to the qubits because this quantum hardware is a physical system with far more capabilities than just being simplified as a qubit system, okay? And therefore, you can also have the gate to the system. For example, in a trapped ion system, you can have qubits, but you can also have the phonon degrees of freedom that are bosons. You can couple the spins to the phonons, you can couple the phonons to themselves, and you still have your qubit-based operations as before. So you're kind of expanding your gate set, you're expanding your degrees of freedom, and you can actually take advantage of the natural features of the quantum hardware, and still ask the question of now, how do I decompose my time evolution operator in terms of these more expanded sets? Again, this is an example of, let me just skip this. This is just saying that if you just want to do a digital-based, qubit-based computing, this is a complicated circuit for the Schrödinger model. You need millions of entangling gates to perform an operation like this. But if you actually do this analog digital hybrid approach and use or take advantage of the phonon degrees of freedom in the system, then your circuit is simplified as this. This is much more simplified circuit. The operations are pretty natural to the system already, so there's no problem in implementing those. And in fact, you get polynomial scaling improvement, which is not exponential, but it's still a very large factor. So this is exciting. And in fact, with my collaborator, Norbert Linke, and the group lab, we're actually now looking into implementing some simple quantum field theory simulations using both qubit and the phonon degrees of freedom to show really the power of this kind of approach in simulating gauge theories. Let me also skip this part of the talk, and then definitely I'll skip all these examples that I had to show that there's been progress in all sort of QCD inspired problems, from scattering, collision, thermal observables, phase diagrams, dynamical phase transitions, transport properties, entanglement. So this is really sort of showcasing a lot of interesting work that our community is producing in trying to understand QCD observables from the perspective of quantum simulation and quantum entanglement. You can ask me about those slides. Unfortunately, I didn't get to talk about them, but let me just talk about this very last slide that I hope you agree with me that there is a long way to go to get to QCD, but we know what to do. And as I said, if one thing we learned from the successful conventional lattice QCD program using classical computers is that theory, algorithm, and experiment collaborations will be the key. And it's even more important in the quantum computing era because these computers and simulators are themselves physical systems. So as physicists with real world problems, we have to understand the properties of these physical systems and be able to match our problems to the capabilities of the system so that we can make progress faster. With that, these are my collaborators in the quantum simulation projects, not only nuclear physicists, but also AMO scientists, quantum information science and computer scientists, condensed matter physicists. It's a very multidisciplinary program. A lot of people are interested in the problem of quantum simulating lattice gauge theories and even nuclear effective field theories. So I'm really enjoying talking to a range of very interested and talented scientists, a lot of junior scientists in particular, and to really push the frontiers of this research, and even more collaborators, and also thanks to the funding agencies that are interested in supporting this kind of research. Thank you very much.
Thank you for the next talk. So I think we come to the question.
Sounds good.
There is no question in the chat box. So I think people can raise hand directly to ask questions by clicking the button reactions. Yes, Thomas, please.
Hi, Zohreh. I'm sorry, I was also going to go back to kind of Bernd's question, which is, so in the quantum chemistry community, people are thinking a lot about these kind of hybrid calculations where you actually do a large fraction of your problem on classical computers and then the sort of strongly entangled bit quantum computer. And in QCD, the difficulty somehow seems to be that indeed we've never actually gotten the classical Hamiltonian methods to work. All of the classical work is on Euclidean path integrals, and that seems kind of orthogonal to Hamiltonian methods. So do you think that we should go back to classical Hamiltonian methods as well?
So I mentioned two things. First of all, we didn't. The reason that Hamiltonian method didn't work was really sort of, to me, it was computational. Okay. Our papers on U1, SU2, and even SU3 lattice gauge theories with hundreds of sites where they properly take the infinite volume limit, continuum limit, the bond dimension limit, which is something particular to this tensor network calculations, and really compute physics out of these computations. So they are proper Hamiltonian simulation calculations. Not in higher dimensions, they're usually in 1+1D, and there are recent papers on 2+1 and 3+1 for abelian gauge theories, but they are really proper computations. So number one. Number two is the fact that we still can use our Euclidean path integral computations to learn about the Hamiltonian. So for example, we need to do a scale setting, right? In the same way that we have to set the physical scale for a lattice QCD computations and a path integral approach, we have to also set the physical scale in our lattice gauge theory Hamiltonian approach. So there are now ideas about how to define this properly. For example, if you are performing a Euclidean computation that gives you sort of a continuum limit with an action, you can go through this method of transfer matrix and derive the corresponding Hamiltonian. In the same way that we can add improved operators to our action to be able to eliminate the leading lattice spacing effect or make them smaller in size by tuning their coefficients through the Zemansic improvement program, we can actually then turn them through the transfer matrix methodology to a Hamiltonian and kind of figure out what are those improved operators that you have to add to your Hamiltonian so that you can recover the continuum limit more or faster. Okay. At each step of the way, there is sort of a part of the community. So for example, the Fermi Lab, there are papers on how to perform renormalization continuum limits of Hamiltonian gauge theories, and what they're sort of advocating for is that if at each step of the computation, you have a direct mapping between the Euclidean lattice gauge theory using path integral and the Hamiltonian lattice gauge theory, and then you can actually perform this continuum limit and scale setting rigorously. And in fact, they have shown this in a couple of papers. I have not personally worked on the problem of renormalization continuum limit, but our community does, and there are papers about that. So again, another question you may ask is that if I trotterize my time evolution operator, there are going to be errors associated with that. What are those errors, right? What kind of operators are associated with those errors, right? Whether or not they break the gauge invariance, and they do, and then how do they sort of affect the continuum limit? Again, there are studies like that in the community. And again, the way that people are thinking about it is that if I perform my sort of path integral approach in the same way and kind of introduce a digitization of sort of e to the is similar to the Hamiltonian formulation, you can actually find a mapping between the transfer matrices of the two approaches, and therefore make sure that you recover the same continuum physics that your path integral Euclidean approach does it for you. So this is kind of as much as I know about this kind of renormalization program. As I said, I haven't worked on this person, but this is something that the committee is trying to build rigorously by this sort of mapping between the Euclidean approach.
Thank you.
Sure.
Okay.
We've also got one more point. The other thing is that we do also take advantage of classical computations to facilitate quantum computations. I mean, no difference here, right? I mean, for example, if you have a method that will give you a good approximation to your initial state classically, we can actually use that. We don't necessarily know how to do this for QCD yet, right? Of course, we know a lot about QCD structure from lattice QCD computations, QCD spectrum, the spectral gaps for the proton and all the other low energy states, all of these things we know, right? The question is, how do we build information about these states using our experimental or classical lattice QCD simulations into the state preparation step in Hamiltonian formulation? These are the kind of things that we're exploring for simple models, but it's still not quite for a QCD.
Okay, there is another question from Yi.
Yeah, hi. Yeah, thank you so much for the presentation. So my question is also like general questions. So now we know that the topological objects in QCD and also in gauge theory in general are very important to understand the vacuum of the QFT, like instanton, are very important. So my question is, suppose I do the quantum simulation, do you know any examples that we can really describe the topological objects like the instanton or something like that?
So I don't have an exact example for the question that you're asking. Let me try to go to maybe the closest I can think of about exploring a topological property is kind of this paper with my former postdoc and the collaborators. where we looked at sort of a dynamical phase transition. In the lattice Schwinger model, it turned out that there's kind of a topological order that you can define in a sort of dynamical phase transition. And in fact, what we advocate for in this paper is that, in fact, if you have features in the gauge theory that are topological, usage of the quantum computers in the near term is a really sort of justified first applications for exploring this kind of properties. This is kind of a plot that that is kind of very revealing on that regard, because if you have a topological order in your gauge theory, and we can talk about the physics of this feature that we're looking at here in another time, but the point being that if you have sort of a topological order where you have sort of a quantum number that is, for example, either 0 or another integer, even if you have severe noise in the hardware, this is a very sensitive quantity. It's either 0 or 1. So it's very sort of robust quantity to give you information about sort of the phase transition that are of sort of this topological type. So indeed, if there is such features in your theory and you do your mapping of degrees of freedom and the mapping of the Hamiltonian properly, you still are going to have the same physics in your Hamiltonian simulation. Okay, so we're not going to lose them. And in fact, our argument here is that for quantities of this type, the use of quantum computers, even if your algorithms are not perfect or hardware is not perfect, they are actually good, still very give you very reasonable answers because you have sort of this robustness in the observable. I don't know if that answers your questions, but my point being that if you do your mapping of the theory properly and you're not breaking symmetries and so on in a significant way, you are still going to recover even topological properties of your field theory. That's my opinion.
Okay, thank you. Sounds encouraging.
Sure. And I should have, yeah, this is not to be released. This was in fact released a few months ago. I should have updated this reference. So there's now an archive number for this. I can let you know if you're interested in. I think this is kind of an important point, and I'll mention this to this community, because for a long time when we think about phase diagram of QCD or a strong interaction physics, we're kind of thinking about a static phase diagram. Now in condensed matter, other communities, quantum many-body community, there's a subject of dynamical phase transition and dynamical phase diagrams that is very interesting, and kind of asking questions about, as a function of time, the system goes through different phases and phase transitions. And then you can also define things like critical exponents and universality classes for those dynamical phase transitions and critical points. And this is something that is way unexplored in our community, right? You can imagine that for QCD physics and heavy ion collision physics, what is the notion of a dynamical phase diagram, right? That we have to explore, and we haven't really sort of explored questions like this because, again, we didn't have access to first principle Hamiltonian evolution, Hamiltonian simulations in our problems. So I think this is really exciting, and we have to start thinking about phenomenological signatures of things of this nature that other communities are thinking about and exploring.
Okay, I didn't see other questions. I have a question. Do you have some comments on these comparisons between the time evolution and this VQE algorithms? I saw you have used this time evolution a lot, and in many other studies, they use VQE at this stage, right?
Yes. So a VQE is very good algorithm for learning about static properties of the system. Although there are VQE algorithms that will tell you how to do time evolution, right? You can still do kind of sort of an optimization problem to build your time evolution operator. I didn't talk a lot about sort of the spectral properties, or if you're interested in ground state energy and so on. performing a VQ algorithm is very, very natural, because no matter whether or not you have the right ground state energy, right, you are trying to make a non-trivial state in which you can perform the expectation value measurement of your Hamiltonian, and then using your classical optimizer to optimize the parameters of the circuit that builds that non-trivial, complicated, entangled state, and then do this back and forth to be able to get sort of a good estimate to both ground state energy and the state, right? Of course, this is very important. I didn't touch up on this a lot because I didn't quite talk about observables, right? I mean, the observable part is really sort of these are the slides that I kind of prepared, but definitely, I think that's sort of one of the near-term approaches is really sort of this hybrid classical computing approach, and we have to take advantage of it. But I think in the far term, as I said, motivated by the kind of problems that we have in QCD physics, we really want to shed light on the real-time evolution in nuclear physics. This is sort of the goal, and that's why I kind of focused a lot on that aspect. But that being said, we really need to have better methods to do a state preparation, because if we want to do an honest to God high energy collision process, we have to be able to sort of make states that resemble the states that we have in our experiments, collision experiments, right? The protons or a large nucleus. And this is, we are nowhere close to being able to know how to do this, in particular, how to do this efficiently for QCD and non-trivial states. So the best that we can do at the moment is to create non-equilibrium conditions using quantum experiments. So sort of this plot that I showed over here is kind of based on the fact that, for example, in the Schrödinger model, you prepare the ground state of the theory in the positive mass, and then you quench your Hamiltonian by changing the mass to become negative mass all of a sudden. And then you ask the question of sort of this dynamical phase transition as a function of your theta angle, because really sort of there's a connection between the sign of the mass and the theta angle quenched from 0 to pi in the Schrödinger model with the theta term. So these are simpler because the initial states turned out to be in the computational basis product states. These are very easy to prepare. And so on. Although for this problem we had to do more because we wanted to work in position space and momentum space for different parts of the circuit. But in any case, at the moment, because of the limitations of the hardware, we're limited to simple initial states, and then the quench problems because these are simpler. And still, they would create non-equilibrium conditions for us. And we are able to learn some interesting phenomenological features in non-equilibrium physics of these gauge theories. If we really want to do something that mimics, for example, heavy ion collision experiments, we have to do more complicated initial states and create an exact non-equilibrium conditions that we deal with in this experiment. So we are still not there, but we're making progress in simple models and creating hadronic wave packets with certain momenta and energies and colliding them with each other and so on. I didn't really talk about these, but this is kind of the slide I wanted to kind of talk about, to say in simple spin models or Z2 gauge theories, people are thinking about how to create these kind of wave packets for quantum simulators and what kind of information in real time we can gain out of these high energy scattering processes. So that's really the next level of developments that our community is focusing on at the moment.
Okay, thank you.
Sure.
Any other questions from audience? If no questions, I think we can stop here and thank Zohreh again.
Thanks very much. Thanks a lot for the very, very good discussions and good questions. I hope this was useful.
It was. Thank you.
Yes, thank you so much.
Of course. Have a great day.
Yes, you too. See you soon, and also see you all for the next seminar.
Great.
Bye.
Thanks a lot. Bye-bye.
Bye.
Bye.